So this will constitute an AC circuit. The circuit elements in an AC circuit are resistance, inductance, and capacitance. Now we have to understand what is resistance. Now resistance is the opposition offered by the conductor to the flow of current through it. It can also be defined as it is the property of the material by virtue of which it opposes the flow of current through it. It is represented by R and is measured in ohms. Now this is a resistor, the device, and here this is the way the resistance is represented when you have to write in a circuit. Now the value of the resistance depends upon the nature of the conductor, the length of the conductor, area of cross section, and temperature of the conductor. So here in this figure, you can understand the concept of resistance. Whenever current has to flow in a conductor, then you have to apply an voltage. When an voltage is applied, the current flows in the conductor. We know that current is nothing but the flow of electrons. But the property of the material of the conductor opposes the flow of this current. The property of the material of the conductor opposes the flow of current. Now this property of the material by virtue of which it opposes the flow of current is called as resistance. So in the circuit here a simple circuit, you can see that if the resistance is going to be high, then the current is going to be less. On the other hand, if the resistance is low, then more current or high current will flow in the circuit. So which is shown by the thickness of the lines here. Current is given by V by R. You have already studied the Ohm's law. V equals I into R, and the current is given by V by R, or resistance is equal to V by I. So if the resistance, we can observe from here, it is an inverse proportion between the current and the resistance. If the resistance increases, then the current decreases. Or if the resistance decreases, then the current increases. So we can see that it is an inverse proportion. Next, we have to understand what is inductance. Inductance is the property of the coil by virtue of which it opposes any change in the current flowing through it. It is represented by L and is measured in henries. So, if you take a long conductor and you wind the conductor on a bobbin like this, then it will form a coil. So you can see this is a cylindrical core on which the conducting wire is wound, and this will form an inductor. The symbolic representation of an inductor is as shown here. It is in the form of a coil here. And here the figure shows the variety of inductors which are used. So inductance is the property of the coil. Now this coil, It is the property of this coil by virtue of which it opposes any change in the current flowing through it. So you can see here the current is entering the coil, it flows through the coil and it will exit at the other end. Now if we try to change the amount of current that is flowing through it, then the property of this coil will try to oppose that change, and that parameter or property of the coil is called as inductance. Now, we just have to understand what is this inductance actually. So here consider a coil and a current is flowing through the coil. Whenever current flows through the coil, a magnetic field is set up around the coil. So when current flows through the coil, surrounding the coil, a magnetic field, an electromagnetic field is going to be set up surrounding the coil. Now, we can understand the functioning of an inductor through this graph here. You can see here we have plotted current versus time. Now, as the time is increased, the current goes on increasing in the coil. As we increase the current through the coil here, the current goes on increasing, and thereby the magnetic field also goes on expanding around the coil. After some time, it is going to become constant. The current is going to become constant. That means to say the magnetic field that is formed around the coil has reached a steady value. It has reached a steady value. Now here in this graph, you can see that the current is going to take some time to build up the magnetic field around the coil. So similarly, if we are going to stop the flow of current through the inductor, then it takes some time to come back to zero. For the current or the magnetic field to collapse, it is going to take some time to completely collapse. So, any change in the current here that is going to flow through the inductor is going to be opposed by the coil, and that property of the coil is called as inductance. Next, we'll move to capacitance. Now, capacitance is the property of a capacitor due to which an voltage is built up in the capacitor, which opposes the applied voltage and in turn the current flowing through it. It can also be defined as the capacitance is the capacity of the capacitor to store electric charges in it. It is represented by C and is measured in farads. So you have to understand here, capacitor is the device which stores electric charges, whereas capacitance is the property of the capacitor to store electric charges in it. So this is a figure of a capacitor, and this is the symbol of capacitor, how it is represented in a circuit. And here again we can see a graph here, voltage versus time. So when the capacitor is charging, so you can see this is an exponential charging. So slowly the charges build up in the capacitor, and with time it is going to reach a steady value. Similarly, when the capacitor is discharged, you can observe here slowly the charges is going to die down or decay. So this is another representation of charge versus time. This is capacitor charging and this is capacitor discharging. Next, we have to understand what is inductive reactance. It is the opposition offered by an inductive coil to the flow of alternating current through it due to its self-inductance is known as inductive reactance of the coil. It is represented by XL and is measured in ohms. So, whenever there is a coil and a current flows through it, when an alternating current flows through it, there is an opposition to the change of current flowing through the coil. That is due to the self-inductance of the coil. So that property of the coil is known as inductive reactance. So inductive reactance is given by XL is equal to 2 pi FL ohms, where F is the supply frequency in hertz and L is the inductance in henries. Capacitive reactance. Now this is the opposition offered by a capacitor to the flow of alternating current through it due to its capacitance. It is represented by XC and is measured in ohms. And capacitive reactance is given by the equation XC equals 1 by 2 pi FC ohms, where F is the frequency of the supply in hertz and C is the capacitance in farads. So we have to learn the definition of impedance. Impedance is the total opposition offered by an AC circuit to the flow of alternating current through it. It is represented by Z and is measured in ohms. So Z equals E by I, where E is the voltage in volts, I is the current in amperes, and Z is the impedance in ohms. So it is a total opposition offered by an AC circuit to the flow of alternating current. Just like resistance in case of DC circuits, it is impedance in case of AC circuits. So we have to study what is single phase AC circuits. An AC circuit which operates on a single phase power supply is called as a single phase AC circuit. Now a single phase AC circuit may contain either one or two or all the three of the circuit elements, namely R, L and C. So here you can see different figures here. Now here this is a single phase supply where there is only resistance in the circuit. Here again there is only inductance in the circuit. Here there is only capacitance in the circuit. Here in this circuit it is a combination of resistance and inductance. In this case, it is combination of resistance and capacitance. And here, all the three elements, that is resistance, inductance and capacitance can be present in the circuit. So this can be referred to as RL circuit. This is referred to as RC circuit. And this is RLC circuit. Whereas this is a pure resistive circuit. This is a pure inductive circuit. and this is a pure capacitive circuit. So all of them are here shown here are working on single phase supply. Now we will understand what is a pure resistive circuit. Now this circuit contains only resistance, that is only a resistor is placed in the circuit. Resistor is the device. Resistance is the property of the material of the resistor. So here you can see there is only one resistor placed in the circuit, and the impedance of the circuit is given by Z equals root of R squared, that is nothing but R ohms. That is, it is equivalent to resistance in case of DC circuits. Impedance is equivalent to resistance in case of DC circuits. Now, here you can see in a pure resistive circuit, we have considered the two alternating quantities, voltage and current. So here, this is E, the voltage wave, and this is I, the current wave. Both the quantities are increasing from 0, reaching a peak value simultaneously, and again they are reducing to 0 value, and again increasing in the negative direction, building up to the peak value, and again coming back to 0 simultaneously. That means to say there is no phase difference between the voltage and current. Both of them are increasing, reaching the peak and reaching the 0 value simultaneously. Only difference is seen here in their amplitude. So when we represent in terms of vectors, you can see that the current is overlapping the voltage vector. That means there is no phase angle difference between the two alternating quantities. Now this is a characteristic of a pure resistive circuit. Next, we'll see an RL series circuit. So the name indicates RL. That means in the circuit there is a resistance as well as an inductance which are connected in series. So a resistor and an inductor is connected in series, and the impedance of such a circuit is given by Z equals root of R squared plus XL squared, and the unit of impedance is ohms. So resistor and inductor is connected to the single phase supply here. Now we will understand how the alternating quantities, that is the voltage and the current, behave in case of an RL series circuit. So you can observe here, this is the voltage wave E. This is the voltage wave which is in thick line, and here the dotted line represents the current. We can see that the two quantities are not starting simultaneously. First, the voltage wave has started, and after some time the current wave is starting. Similarly here, the voltage wave has already reached a maximum value, whereas the current is going to reach the maximum value after some time. Now, there is a angle difference between the two alternating quantities, which is shown as theta here. So that means to say the two alternating quantities are not reaching their zero and maximum values simultaneously or at the same time. So when we take the vector representation here, you can observe here. So this is 0. So from here, you can see this is the current I and this is VR. VR is the voltage across the resistor. VL is the voltage across the inductor. So in a resistor, we have already learned that the current is in phase with the voltage. So here you can see that this is the voltage vector, this is the current vector. Both of them, this is the current vector and this is the voltage vector. So both of them are overlapping here. That means to say there is no phase angle difference between them. And here you can see VL, that is the voltage in the inductor, which is given by I into XL. I is the current flowing through the circuit and XL is the inductive reactance of the inductor. So VL equals I into XL, and in case of a pure inductive circuit, then the voltage leads the current by an angle of 90 degrees. So here that is why the voltage is shown to be at an angle of 90 degrees with respect to current. But the circuit considered here is a combination of resistance and inductance. It is neither a pure resistive circuit nor a pure inductive circuit. So it is a combination of both. So we will have to take the resultant here. So when we take the resultant, so OA is the resultant, which is equal to E given by E is equal to I into Z. Next, we'll study a series, RC series circuit. So the circuit contains a resistor and a capacitor which is connected in series. So you can observe here, this is a resistor and there is a capacitor which is connected in series. And the impedance of the circuit is given by the equation Z equals root of R squared plus XC squared. And the unit of impedance is ohms. So let VR be the voltage across the resistance and VC be the voltage across the capacitor. I is the current flowing through the circuit and E is the single phase supply. Now let us study the wave diagram here. Now the thick line here represents the voltage E, that is the supply voltage here. It represents the voltage E, and the current I you can see is represented by the dotted line. You can observe here also the current and voltage is not reaching the zero and the maximum values simultaneously. The current and the voltage is not reaching zero and peak values simultaneously. In this case, you can see the current has already started. Voltage is yet to start from here 0. Here, the current has already reached the peak value. After some time, the voltage is reaching the peak value. Here the current has reached 0, whereas at the same instant of time, the voltage is yet to reach 0. That means to say there is a phase angle difference between the voltage and current. Now, how is this phase angle difference? In this case, the current leads the voltage. So, in the previous case, in an inductor, we saw that the current lags the voltage, or the voltage leads the current. Whereas in this case, the current leads the voltage. Here you can see the current is leading. First it is starting, after some time the voltage wave is starting. So the current is leading the voltage. So when we represent here in the vectors, you can see this. When only we consider a pure resistive circuit, then current and voltage overlap each other. That is, they are in phase with each other, because in a pure resistive circuit, there is no phase angle difference between the voltage and current. And VR is equal to I into R. When we consider a pure capacitive circuit, that means to say there is no resistance. Let us say there is only capacitor in the circuit. Then in that case, the voltage lags the current by an angle of 90 degrees. It lags by 90 degrees, or current leads the voltage by 90 degrees. Either ways you can tell, current leads the voltage by 90 degrees, or the voltage lags the current by 90 degrees. And the voltage across the capacitor is given by I into XC, where I is the current in the circuit and XC is the inductive capacitive reactance of the capacitor. So XC is capacitive reactance of the capacitor. Okay. But the circuit that we have taken here is a combination of resistance and capacitance. So here we will get a resultant here. This is due to the pure resistive circuit, and this is with respect to pure capacitive circuit. But since it is a combination of both, we have to take the resultant, and OA is the resultant, which represents E, which is equal to I into Z. So here, in case of an RLC series circuit, it is a combination of resistor, inductor and capacitor, all connected in series. You can see resistor, inductor, capacitor connected in series, and across that a single phase AC is going to be applied. And the impedance of such a circuit is given by Z equals root of R squared plus XL minus XC whole squared, and the unit is ohms. So here you can observe here VR is the voltage drop across the resistance, VL is the voltage across the inductor, and VC is the voltage across the capacitor, and I is the current through the circuit. So in this figure wave diagram, you can observe this is the voltage wave and the dotted line represents the current wave. So there is a phase angle difference of phi between the two alternating quantities, that is the voltage and the current. Now let us understand the vector representation. So again we are going to combine all the three vectors that we have studied. So here you can see here, the voltage and the current are in phase with each other. So this will be of the pure resistive circuit. VL is at 90 degrees with respect to I. That means the voltage is leading the current by an angle 90. That means that is the characteristic of a pure inductive circuit. Here, the voltage VC, the voltage VC is lagging the current by an angle 90 degrees. So, this is the characteristic of a capacitive circuit. So, but here it is a combination of all the three, R, L and C. So, when we take all the three vectors here, we have to take the resultant here. OA is the resultant and it is represented as E. Sorry. It is represented as E, and here this is VL minus VC, because we see this VL is along the positive direction, VC is along the negative direction. So when we take it on the same y axis, we have to take the difference of the two. VL minus VC will be the value of this vector here, this here. Now, we have to understand what is phase. Phase refers to the relationship between two sine waves. So, throughout we have been studying, we have considered the two waves to be voltage and current. So, the relationship between two sine waves or signals is called as phase. Now, the relationship between the waves can be in phase or out of phase. So, we have to study explicitly what is the meaning of in phase and out of phase. In phase, when two alternating quantities, that is current and voltage, reach their maximum or zero value simultaneously in the same direction during a period of one cycle, then they are said to be in phase with each other. So the two waves have to reach the zero and the maximum values simultaneously during a period of one cycle and in the same direction. Then they are said to be in phase. So here you can observe here. So the thick line is the voltage wave and the dotted one is the current wave. Both the signals are starting here. That is the zero value. At the same time, they are reaching the maximum value. That is the point A, represented by point A here. So they are reaching the maximum value simultaneously at the same instant of time. Both of them, you can observe, both of them are reaching the maximum value, and at the same instant of time, both of them are reaching minimum value at B. So this is in the positive direction, and likewise in the negative direction also, both of them are reaching the peak value, that is point C, simultaneously, and it is reaching the zero value simultaneously. So the phase angle difference between the current and the voltage is zero. Therefore, you can see here the current vector and the voltage vector are superimposed. That is, they are lying one on the other. There is no angle between them. The angle, phase angle is zero. So they are said to be in phase. So next we have to understand what is out of phase. When two alternating quantities do not reach their maximum or zero values simultaneously in the same direction during a period of one cycle, they are said to be out of phase with each other. So let us study through wave diagrams the meaning of out of phase. So here the alternating quantities, here you can observe there is the voltage wave here, the dotted one is the current wave. So both these are not reaching the zero and the maximum values simultaneously. In this case, the current wave has already having some value, whereas the voltage is at zero. And here the voltage has reached the peak value, whereas the current is yet to reach the peak value. That means to say there is a phase angle difference of say around 30 degrees here. So in the figure you can see the vectors. This is the voltage vector, this is the current vector, and the angle difference is around 30 degrees. That means the current is leading the voltage here. The current is lagging the voltage here. So you can observe here, so it is behind, so it is lagging. Now in this figure you can see again this is an voltage wave and this is the current wave, whereas the current here is leading the voltage. That is, it has already started, it is already reached the peak, whereas the voltage is yet to reach the peak. So there is an angle theta difference between the two waves here. So this is one more representation here to make you this is where both the in phase and out of phase are shown together so that you can understand better. So the voltage and current you can see starts, reaches maximum, reaches minimum simultaneously. So this is in phase. Here you can see there is a phase difference of 90 degrees. That is, the two voltage waves here are out of phase by 90 degrees. And this is here, the two waves, voltage waves are 180 degrees out of phase. So if this is increasing in the positive direction, the second voltage wave is increasing in the negative direction. So they are totally out of phase by 180 degrees. So AC quantities, that is the current and the vector voltage, are vector quantities. They have both magnitude and direction, and hence they can be represented as vectors, and most of the times it is assumed to be rotating in anti-clockwise direction. Now a phasor is a rotating vector. Vector represents quantity and direction, that is both magnitude and direction, whereas a phasor represents quantity, that is a magnitude, and displacement measured in counterclockwise direction or anti-clockwise direction. So that is the difference between the vector diagram and a phasor diagram. In a vector diagram, we have the quantity and the direction. In a phasor diagram, we have quantity and displacement. That is, an angle representation is shown there. To take a summation of what we have gone through. So if the load type is of resistance, we can see here that both current and voltage waves are in phase. So you can see this. The blue is the current vector and the red is the voltage vector. Both of them are in phase. If it is a pure inductive circuit, then the current lags the voltage by 90 degrees. Current lags the voltage by 90 degrees. Current lags the voltage by 90 degrees. And in case of capacitance, you can observe the current leads the voltage by 90 degrees. So you can see current leads the voltage by 90 degrees. So next, in a pure resistive circuit, so we have just now studied, current and voltage are in phase with each other. So in case of an RL circuit, here you can observe in a resistive circuit, the voltage and current are in phase, and whereas the voltage across the inductor, that is VL, is at 90 degrees, and since it is a combination of both, we have to take the resultant. OB is the resultant, where V is equal to IZ. So in case of inductive circuits, the current lags the voltage by an angle phi. So this is the very important, you have to understand. In case of RL circuit, the current lags the voltage. So this is the resultant voltage. The current lags the voltage by an angle phi. So you can see here also in the wave diagram, there is a phase angle difference of phi between the voltage and the current. Now, in case of an RC circuit, so let VR be the voltage drop across the resistance. VC is the voltage across the capacitor, which is connected across a AC supply. And when we plot the wave diagram, we have learned that the current in a capacitor leads the voltage, or voltage lags the current. So the current leads the voltage. So what you see in red, you can see that the current is leading compared to the voltage. In vector representation, you can see this phasor representation. You can see this. This is in case of a pure resistive circuit, where the current and the voltage are in phase. They are overlapping here. So no phase angle difference. And here we see, what you see, it is making an angle of 90 degrees with respect to the current. That is in case of a pure capacitive circuit. Since it is a combination, we have to take the resultant. So OB is the resultant, and which is V equals IZ. So in case of RC circuit, the current leads the voltage by an angle phi. So here you can see, this is the voltage, this is the current. So here, with respect to the resultant, the current is leading by an angle phi. So in case of an RLC circuit, we have all the three elements, and this will be the representation here. So you can see this is the blue line is with respect to the resistance here, and this is IC, that is the current in a capacitor leads, and here the current in an inductor lags. So this is the vector representation. So you can see that where here AB is equivalent to VL minus VC, where VL equals I into XL and VC is I into XC. So in case of a series RLC circuit, the current lags or leads the voltage depending upon whether XL is greater than XC or XC is greater than XL. If XL is greater than XC, implies it is more an inductive circuit, and therefore the current lags the voltage. In case of XC being greater than XL, it implies it is more a capacitive circuit. That means the current leads the voltage. So next we have to understand power factor. What is leading power factor, lagging power factor, unity power factor, zero power factor, and power. A power factor is defined as the cosine of the angle between the applied voltage V and the total current I in the circuit. It is just a number and is always less than 1. So it is written as, power factor is written as cos phi. So as per the Indian electricity rules, it should always be greater. Preferably, it should always be greater than 0.9 and it is always less than 1. Now, we have to understand what is this power factor. See, whenever we are consuming the power, how much of it is useful power and how much is going to be the wasted power. That is what we are not going to utilize. So here the power factor is always a ratio of working power divided by the total power. So which can be understood very well with this figure. You can see here, this is a coffee mug here. So in the coffee mug, you can see what is the amount of coffee that is present and what is the amount of froth that is the at the top of the coffee. What is the froth at the top of the coffee? Now here, the actual coffee, the amount of coffee represents the real power. And whatever is the froth, which is not the coffee, actually, it is just the foam at the top of the coffee, that represents the reactive power. And the total of this will give you the total power. That is, reactive power plus the real power will give you the total power. So actually, when we say we are going to drink coffee, how much of it is actually coffee that we are consuming? It is only this much. You can see here in brown, it is only this much. That means to say, it is an analogy that is struck here. So that means to say, this constitutes the real power. And whatever the froth on the top of the coffee is not exactly the coffee that will be consuming. So that will constitute the reactive power. So it is not useful to us. The froth is not useful to us. So when this is represented in a power triangle, you can see here, this is the phase angle. The true power or the real power is measured in kilowatts. Now, this is the vertical, the perpendicular one here is the reactive power, which is measured in VAR, that is volt ampere reactive. The bigger unit of this is kVAR, that means kilovolt ampere reactive. Similarly, here also watt is the smaller unit and kilowatt is the bigger unit of power. And the resultant here of this is the apparent power, which is measured in VA, that is volt amperes, and the bigger unit is kVA, kilovolt ampere. So we know that power is given by VI cos theta, or cos theta from here can be found to be cos theta can be found to be power by VI. So we have just shifted this VI here. So cos theta, which is the power factor, is given by the ratio of power divided by you can see here it is power divided by VI. We know the unit of power is kilowatts and the unit of VI is kVA because unit of voltage is in volts, unit of current is in amps. So it is V into A. Since we are considering the bigger units, we are taking kilowatt by kVA. So you can observe here kilowatt by kVA. That means to say the power factor is the ratio of true power by apparent power. So the power factor must always be high. It should be nearer to 1. Greater than 0.9 is always preferable. Because if power factor is going to be less, then there are lot of disadvantages. There are a lot of disadvantages like you will have to use bigger size of the conductor, then you have to use larger rating of the machineries and equipments, then there will be increased copper losses and also the regulation will be poor. So thereby it is always preferred that the power factor must be greater than or equal to 0.9. Now we have to understand here what is leading power factor. If the current in a circuit leads the applied voltage by certain angle, then the circuit is said to have leading power factor. So the current has to lead the applied voltage. So just now we have studied all the different types of circuits. So the current has to lead the circuit means that happens only in a capacitive circuit. So therefore a capacitive circuit has leading power factor. Now if the current in the circuit lags the applied voltage by a certain angle, then it is said to have lagging power factor. So that too we have seen. So where the current lags is in case of inductive circuit. Therefore, inductive circuit has lagging power factor. Capacitive circuit has leading power factor. So in the figure, in the vector representation, you can understand here. This is the applied voltage in blue and this is the current in red. You can see that if you assume anti-clockwise direction of rotation of the vectors, you can see that first there is the voltage and following the voltage, the current is present. That means the current is lagging behind the voltage by an angle theta. Therefore, it is lagging power factor in such a circuit. So, in those circuits where the current lags the voltage, it will have lagging power factor. So, where do we see that? It happens in inductive circuits. In this case, you can see the voltage in blue and this is the current in red. The current is ahead of the voltage. Current is leading the voltage by an angle theta. So those circuits in which the current leads the voltage, it will have leading power factor. So capacitive circuits have leading power factor. Next, we have to see what is unity power factor. So, in a case of a pure resistive circuit, the current is in phase with the voltage. There is no phase angle difference between them. It is zero. The angle between them is zero. So, here you can see this is the voltage, this is the current, no angle between them. That means to say what? Phi is equal to 0. So, now what is the power factor? Power factor is nothing but cosine of the angle between the voltage and the current represented as cos phi. So in this cos phi, for phi, if you are going to put it as 0, because here we see that the angle between them is 0. So put 0. We know that cos 0 is 1. That is unity. So a pure resistive circuit will have unity power factor. So if you plot the wave diagram, you can see the voltage and current will be in phase with each other. Therefore, the power factor will be 1. Next is zero power factor. Now, if the current in the circuit leads or lags the applied voltage by exactly 90 degrees or pi by 2 radians, leads by 90 degrees or pi by 2 radians. So we have seen that. So we can, it is 90 degrees electrical or pi by 2 radians, then that circuit is said to have zero power factor. Power factor in case of a pure inductive and a pure capacitive circuit is 0. So here you can see, here the current lags the voltage by 90 degrees. So if the angle of rotation here, omega, what you can see, if the angle of rotation is taken to be anti-clockwise, then voltage is already reached a peak value, whereas current is lagging behind. So current lags the voltage by 90 degrees. So as soon as you see the figure, you can make out it is an inductive circuit. So it is in case of inductance. Whereas in case of a capacitive circuit, if you take anti-clockwise direction of rotation of the vectors, so you can see that the current is leading the voltage by 90 degrees. Okay, so we know that power factor is equal to cos phi. So if the angle phi is taken to be 90 degrees, as here, as in the case of a pure inductance or a pure capacitance, its value is found to be 0. That is why the power factor of a pure inductive and a pure capacitive circuit is said to be 0. So finally, we come to understand what is power. Power is defined as the amount of work done by an electric current per unit time. So it is work done by an electric current per unit time. The unit of power is watts, the smaller unit, or the bigger unit is kilowatts. Power consumed by a single phase AC circuit is given by the product of the voltage applied to the circuit and the in-phase component of the current in the circuit. So here power is equal to E into in-phase component of the current, that is power equals VI cos phi watts. So the current can be resolved into two vectors. One is along the x-axis and another along the y-axis. The component along the x-axis will represent I sin phi and the component along the y-axis represents I cos phi. So here in case of when we take for power, we always consider P equals E into I cos phi watts. The unit of power is watts. Thank you. If you have any question, you can ask.